Works? Yeah, great. So thank you very much. So I will continue the talk from yesterday, and just I will spend 5 minutes on recalling what happened yesterday. And as you may remember, I was working with a partially symmetric tensor in some tensor products of a bunch of symmetric spaces. For brevity, this is denoted by S twiddle D. And there was this polynomial ring that's kind of coordinate ring on this on the underlying product projective space. There was a polarity action that I defined, well, in a lame way with using coordinates and not explaining everything in full details. Then Bernard asked if I can do it without coordinates, and this is the way to do it without coordinates. So what you do is you take the dual vector space to S. This is homomorphism from S to K, K-linear homomorphism from S to K. And you can interpret it as a divided power series ring. Well, maybe it should be divided power series ring. And then you define the apolarity action on that. So you take anything from the S upper star. And then if you take theta hook T, so a result of this apolarity action, well, it should be an element of, again, S star. So it should be a homomorphism. So I should tell you how this homomorphism acts. So I'm taking another element from S, and this is the definition of the action. In this way, well, I used coordinates here, but I can get away with that. But in this way, I don't really need the coordinates to define the apolarity. And exercise is to check that this is exactly the same as yesterday. And then once you do it, this makes this S upper star an S module, because you can multiply by elements of S. And this S twiddle, which is the set of polynomials, so the finite power series, is actually an S submodule. So finite means that there is only finitely dimensional space, subspace of S, on which this homomorphism is non-zero, and it's zero elsewhere, or on the complement. Well, I mean, in basis at least. Okay, and then the annihilator of T was defined as the set of all those guys that kill my T with this apolarity action. And at the end of my talk, I stated the border apolarity theorem. So the border rank of T, or maybe that if you prefer that T belongs to the secant variety, the border rank of T is at most R, or if you prefer the T is in the R secant variety, happens if and only if there exists an ideal in S which has all these conditions. So there was multi-homogeneity with respect to the grading, the grading by ZK, and also, well, its dimension is essentially equal to, most of the time it's equal to R, unless this space does not allow it because it's too small. And then there was also condition on the containment in annihilators. So the first three conditions are the main ones. And then there is the difficult one, which we don't have too many tools to check, which is this condition that I is a limit of ideals of points. Okay, so I will keep that thing over there. I will need it a little bit later, but for now, I want to introduce group actions into this picture. So, well, T is in this tensor space, S twiddle D, and there is an action on the tensor space by GL A1 times GL A2 times times GL AK. So there's a product of linear groups that acts on the tensor space. And maybe, well, the many interesting tensors, including matrix multiplication, which was discussed both by Matthias and by Tobias yesterday afternoon. So the matrix multiplication has a lot of symmetries. There is a large subgroup of these groups which preserves the matrix multiplication tensor, and therefore, well, I will define the maybe let me call this guy G, and then GT is equal to the set of all those elements in G, such that G times T, well, typically I would say is equal to T, but for convenience I would rather choose that it's equal to lambda times C. It doesn't really matter that much for some lambda in the field. Maybe I should stress that this everything on this side, everything in this picture is invariant under the rescaling. So the border rank of lambda T, if lambda is non-zero, is the same thing as border rank of T. Annihilator of lambda T is the same as annihilator of T. Again, lambda non-zero, and so on. So the whole equivalence here, it doesn't see really rescalings. That's why I use this lambda here. Okay, and then this is some group, maybe trivial, who knows, maybe finite. Then I can't add much to my picture if it's trivial or finite. But if it's non-trivial, if the dimension of this group is positive, then I can always find another positive dimensional subgroup, which is solvable. So this means that if I see this group GT as a matrix group, then in some coordinates this matrix group will be, this solvable subgroup will be the intersection of GT with upper triangular matrices. So it's more or less the same, I think, as upper triangular. And well, so if this dimension was positive, then I can always find this dimension B to be positive. And maybe I should say also connected. Otherwise, it's a little bit more tricky. And if you are very, very strongly algebraic geometry oriented, then I should also add reduced, but let me skip this part. Okay, and now why I work with these solvable groups is because solvable groups have this property that if B acts on a, well, in a linear, if B is a solvable linear group, and it acts on a projective variety Y, then there exists Y in Y such that B Y is equal to Y. So it's this solvability allows us to find a fixed point of the action. Well, I don't really want to explain what projective means, but it's equivalent. In topology, it would be equivalent of compact in this setting. So in other words, if you have an orbit, then in the closure we will find some smaller orbit, and you keep doing this until you find fixed point. That's roughly what happens here. And now, how does this relate here to this guy? I can take the given t and r, so t is a tensor and r is an integer, I can define something which, for traditional reason, it's called variety of sums of powers, but let's just call it VSP, with an underline of t and r. And this is the set of all the ideals in S which satisfy all those conditions. So there is multi-homogeneous. Maybe I should stress that this works whenever Y is non-empty. And then this is multi-homogeneous, has this Hilbert function, so dimension of S mod I in all degrees is equal whatever it's written over there. So the minimum of R and the dimension of S d prime. And also I is contained in annihilator of T, and I is a limit of ideals of points. Okay, so the main point is that this is a subspace of the set of ideals satisfying these two conditions, and I can add also that one. And this is known to be projective variety. So this is a subset of something that's called slip R, and this is projective variety. Okay, and also this guy here this ideal being contained in annihilator, it's a closed condition. Therefore, this guy here, so a closed subvariety of a projective variety has to be projective, so this guy is projective. So I might be in this situation here, where Y is equal to this guy over there. So I should stress that this definition here, at least as I wrote it, it does not involve any closure. So the closure is hidden, all the closure part is hidden in this difficult part of the problem. So we have, let me phrase the statement of the theorem. So first I restate the border apolarity. I will leave some space. So T is a tensor. The border rank of T is at most R if and only if there exists, well, if and only if the VSP, the border VSP of T and R is non-empty. Okay. Do you agree with that equivalence of these two theorems? And then I can add if I have, if G and if B and GT are as above, then that the VSP is non-empty, means that the fixed points, well, maybe if and only if the subset of the ideals in VSP TR is non-empty, is this such that the B times I is equal to I is non-empty. So this is the fixed point property. And then this happens if and only if. Well, I can rewrite this whole thing by simply adding one more condition, that also I is B invariant. So there's one more condition that's quite important. Okay. And the way we are using in this talk, at least, the theorem is the following. So I forget the difficult condition. I just ignore it. And then I don't have equivalence. I just have one, not the other implication, sorry. So if I forget this condition, then I have only implication in this direction. Okay. So this is the weak border apolarity that I want to use. And maybe let me give you an example how this works. Well, before I give you an example how this works, I will try to impress you with other people's results. So, so there is a theorem, well, that the border rank of the matrix multiplication, I think this was denoted so this is equal to 7. Well, and again, the upper bound was obtained by Strassen, essentially, by saying that the rank is 7. Then the first proof was by Landsberg I think, in 2005. And maybe I would say that even, well, since this is recorded, I shouldn't say much about that, but even Landsberg is not very happy about the proof from 2005. And well, there was another proof which was highly computational. And using this technology, finding the fixed points, they were able to show Landsberg Connor and Harper, sorry for the wrong order, in 2019, they were able to show that, well, essentially hand-checkable proof, which only required 2 cases to verify, if you take care of symmetries appropriately. And then, well, okay, so maybe that's not very impressive because this is a small matrix multiplication, but also the same method, or in the same paper, they were able to prove that the border rank of matrix multiplication of matrices of sizes 2 times 2 and times 2 times 3 is equal to 10. If you take 2, 3, 3, then it's equal to 14, and 3, 3, 3. Then, well, they did not manage to obtain exact value, but at least they lower bounded it one better than before. So previous was at least 60. And then they also give more lower bounds on this. Right. So the main idea of the proofs for this matrix multiplication is you take exactly the Borel subgroup of the group of automorphisms of matrix multiplication. As you know, the matrix multiplication is invariant under a pretty large group. You can multiply the respective matrices on each side, and you will get essentially the same result, or appropriately transferred matrix. Let's see, how does this work? But I will give you some simpler examples, namely the monomials. Yes. Rank? It's larger. I think, I'm not sure if well, so the rank, I think, for the 3 by 3 matrix multiplication is at most 21 or 20, and at least 18 or something. And it's unknown precise. I don't remember the values for the other guys. But I mean, other than 2 by 2 matrix multiplication, I think it's already known that there is a gap. Or maybe, I'm not sure about that, but it's expected that there is a gap. Okay, so now, for a while, I will use the tensor space, which is simply just symmetric tensor space. And I will discuss monomials here. So a monomial is simply a product of variables to some powers, as you can expect. And then with this x1 up to xa forming a basis of A. And well, obviously it has a large group of symmetry. What is the group of symmetry of a monomial? Do you know? So what can I do to this to at least to not change not to do anything other than rescaling of the monomial? Thank you very much. So you can always, so there is a k star to the A is always contained in GT. And well, as far as I'm concerned, that's the only thing I will be using. Sometimes you have additional symmetries by permuting variables, and That's essentially it in most cases. And then this is actually a solvable subgroup. So this is my B. And then what are the B invariant divisors? B invariant ideals. In the polynomial ring S, which is of alpha 1 up to alpha A. And ideas, what could be B invariant ideals? Hello. So it turns out that these are precisely the monomial ideals. Well, you can easily check that if you have a monomial ideal, so an ideal which is generated by monomials, then it's, well, if you rescale variables, it's still, well, and the function with rescaled variable will stay in this ideal if it was before. And the opposite is also true by decomposing into homogeneous factors, homogeneous with respect to this A-tuple grading. Okay, so we have monomial ideals in a polynomial ring which would contain the annihilator. So, I want to use the apolarity, border apolarity, to discuss this monomials, and then the immediate application of the theorem is that if border rank of T of this monomial is less or equal than R, then there exists a monomial ideal with all those properties. So first of all, dimension of S mod I in degree. Now I can use just 1 degree d prime is equal to the minimum of R, and the dimension of S d prime, and also the ideal is contained in the annihilator of T, which is also relatively easy to compute, which is the ideal generated by alpha 1 to the power B1 plus 1, alpha 2 to the power B2 plus 1, and alpha A to the power BA plus 1. So there is exactly A generators of this ideal, and they are in a very simple form. So you can see that if you derive this monomial B plus 1 times with respect to the first variable, you will get 0, because it's only divisible B1 times, and so on for each variable. So you can easily see that these are all killing IT, but also it's the case that the inverse, this is everything that is in the annihilator will be some combination of these guys with respect to with coefficients that are functions in S. Okay. So what the state of art is that, well, it was known that the border rank of T is less or equal than if you take B1 plus 1 times Bn plus 1 and divide it by any of those. So we just take the product of all except 1, then this is an upper bound for the border rank of T. This was obtained by writing an explicit limit. That's not very difficult to justify. It's always the case. And then well, if you choose the order right, say Bn is the largest. Then you can just use one of those, and this is the same thing as just B1 plus 1 times Bn minus 1 plus 1. Then the expectation was for some time, I mean still is, it's a conjecture I suppose, that this is always the border rank is equal to this number. At least until there were several attempts to prove it, and so far no general proof. So it's the upside down of what was in the other room. And the border apolarity technique, I will show you how it works on an example. So if I take T is equal to x1 times x2, well, let me actually use different notation. My x1s and x2 are now will be x, y, z, and w. So the very simple monomial which has a lot of symmetries, so I will have less cases to explain. But symmetries do not really help in general. I mean, not, at least we can't really exploit this too much. Then we have that annihilator of T is generated by squares. And then I'm trying to use the border apolarity to show that in this case, this is precisely the border rank is equal. So suppose by contradiction that border rank of T is less than 7. This number here is 8 for this particular example. And then what I have some dimensions to write out. I have dimension of Si. So this is a polynomial ring in 4 variables, and I want to write down the dimension of its ith degree. I have dimension of S mod I in degree I. So this number from here, and dimension also of II, which will be just the difference of these two, and dimension of annihilator of T in degree I. And then this is going to be I. So there is this table. I will just go to 4. It should be enough. So this is 1, 4, 10, 20, and 35. This is supposed to be the minimum between this 7 and this number. So it's 1, 4, 7, 7, 7, and it's always 7 from now on. The dimension of II is the difference between these two, 0, 0, 3, 13, and 28. And annihilator is generated by these 4 quadrics, so there is nothing in degree 0, There's nothing in degree 1, and there is also precisely 4-dimensional space of quadrics spanned by these guys. And then there is, I think, 16. So there is each of those, you can multiply each of those generators by a linear form, and there is no relation between them yet. And also here you should have, in degree 4, should be 4 times 10, but now, so there is 4 is coming from the generators and 10 is coming from the number of quadrics, but then you need to subtract a bunch of relations because alpha square, beta square will be in 2 places, the same will be for any pair of those, so you have to subtract 6, and that makes it 34. Okay? And then something happens. Afterwards, I don't care. So what does it mean? That I want to find, well, my goal is to prove that there is no such I that satisfies that, this condition, these dimensions. And it's contained in the annihilator. So, okay, so in degree 0, I don't have to do anything. Well, there is no I. In degree 1, there is no I. But in degree 2, I need 3-dimensional I, and it has to be a monomial. So I need to pick 3 monomials, and the choice I have is limited to those guys here, because it has to be contained in the annihilator. So I need to pick 3 of those, right? And of course, there are 4 ways of doing that. They are all the same, because I did not choose the order. That's why. If it's more complicated monomial, then I need to play a more difficult game. But in this simple case, I have one choice, so I can assume that I2 is span of alpha square, beta square, and gamma square. Okay? Now I go one step forward. So I know that I3 needs to contain the ideal the degree 3 guys contained in here. So this will contain alpha square times anything. It will contain anything meaning any linear form. So this will be alpha cube, alpha square beta, alpha square gamma, alpha square delta. And the same with beta square and then gamma square. So there is 4 of those guys, 4 of those guys, and 4 of those guys, and there is no overlap between them. So there is altogether 12 monomials, and I need 13, so I need to throw in 1 more, right? And the choice I have is among delta square times something. Another monomial from here. The delta square times something can be one of 2 things. So it's either delta cube or it's delta square times, I know, alpha. And there's no difference between beta, gamma, and alpha up to now, before I make this choice. Okay, so if I do this, then I already have that alpha square is in the ideal, beta square is in the ideal, gamma square is in the ideal, and delta cube is in the ideal. So whatever I do for I very large, I will get that I is, in degree I, is equal to Si. Okay, because any large degree monomial is divisible by either alpha square or beta square or gamma square or delta cube. Okay, so this is wrong choice. I cannot take this one because I need the codimension of I to be 7, not 0 in the far I very large. Okay. So this choice doesn't work. So let's go with this one. So now I have I want to look at I4, which already contains, I know what it contains, alpha squared times anything, beta squared times anything of degree 2, beta squared times anything of degree 2, and gamma squared times anything of degree 2. And also it contains delta square alpha times anything of degree 1. So there is 10 of those, 10 of those, 10 of those, and 4 of those. But there are some overlaps. So what are the overlaps? Well, I go from here. If I start from here, there is no overlap between alpha square and alpha square itself. But then if I start going here, then I have alpha square, beta square, which is both here and here. I go here, I have alpha square, gamma square, but also beta square, gamma square, which was already seen before. And here, the only guy that appeared before is the alpha square times delta square. I don't have anything divisible by beta square or gamma square in here. That's the only guy. So altogether, I have 3 times 10 plus 4 and minus 4. 1, 2, 3, 4. If I remove the overlaps. And there is no double overlap. I mean, this is, I think, 30. But if I go back to my table, I was only allowed to pick 28. So I've lost the game, right? Meaning that also this case cannot work. Okay, so as you see, this is some game with integers. You just count the dimensions of some vector spaces, and you can win, or sometimes at least. And we did this systematically. Proving that the border rank of x1 to any power x2 to any power x3, so in 3 variables, is equal to the expected one, so b1 plus 1 times b2 plus 1, assuming that they're ordered correctly, and also some small cases. So I guess the most impressive, at least for us, was just x1, x2, x3, x4, x5, and x6. That has the same, which has the expected border run. But of course, so this one is a theorem proved by an honest writing down on paper, whereas that guy, at least we were unable to do it by hand. We used computer, and the calculation, the very naive code that we wrote was running for maybe 2 or 3 weeks, and then it just checked all the possibilities to exclude. Okay, so that's essentially everything that I wanted to discuss. If you have any questions, then you're very welcome to ask them, and I can answer some questions from yesterday that I've left unanswered, but I can also, I can also report on something slightly different. So, yes, please.
Could you please repeat where this 1477 comes
1477, okay. So this comes from border apolarity. So I'm trying to check if it's possible that this tensor or monomial has border rank 7. So this is R equals 7 case. And I'm trying to use border apolarity. So I'm taking this part of the border apolarity, which says the minimum of R and SD, and this is precisely this number. So this is dimension, so this is the same as here, and this is minimum of 7 and this number here. Right. This row, the second row is the minimum of 7 and the top row. Please.
Do you have any examples for monomials where the ideal actually exists?
No, so we don't have the example like this, and then we've made a naive conjecture that all the monomial ideals with correct Hilbert function will be in sleep, so that this redundant condition. But to the second thing, my student was able to prove a counterexample. So he has a monomial ideal which is not in sleep, and has correct Hilbert function, but it's not in sleep.
But also in the annihilator?
No, that's the issue.
I probably didn't want to say it, but those Jan patterns don't work?
No, well, I mean, Luke was not able, so maybe let me answer this question in more detail. So prior to our work, there were at least two first or second versions of on arXiv which claimed to prove this conjecture, that the border rank is equal to this expected number. And the first one was by Luke Oding, and he was trying to use some determinantal equations to show that. But at some point there were some people found mistakes in this argument, and eventually the whole paper was withdrawn. First he downgraded to just 3 variables case, and then the whole paper was withdrawn. And then there was another approach which essentially was correct, except it relied on another unpublished paper, and this another unpublished paper turned out to be incorrect. So this other approach had also to be withdrawn. So there are some other ideas how to approach this problem. I'm not saying this border apolarity is the ultimate solution, but at least nobody so far has pointed out any combinatorial mistakes in our argument. I don't know if anybody bothered to check it properly, but I think I'm pretty confident this is correct, and I can stand and defend it for now. Okay, so another question? Yes.
So you never require I to be saturated. So what kind of geometric object is I?
So I don't want it to be saturated. I want it to be a limit of saturated ideals of points. So I cannot really say more. So the limit will define a subscheme of the product projective space or projective space in the case of, or in this case, which is smoothable, but it's not. The ideal will be smaller than this. I mean, it's just an ideal, homogeneous ideal. I can't say more for now. I mean, my student Tomasz Mandziuk can say much more, but still it's not, I mean, he doesn't have like complete characterizations in all of the cases. He can do the characterization in maybe in P2 when R is 4 or 5 or something, which is kind of useless for our application, but he has lots of criteria that are not useless for others. So he can say that if some dimension of some space constructed from I2, like I2 squared divided by something or something, in some degree is at least that, then it cannot be in in a limit of ideal of points, and also he has some criteria that say otherwise. So if some things happen, then this must be a limit of ideals of points, but it's not conclusive, because, I mean, except in the small cases. So there's an upper bound, there's a lower bound, and they don't coincide. There's some space in between.
So when you remove this condition of limit of ideals of points, you define another notion of rank.
Yes. Which is very, very weak. I mean, it's
Does it correspond to the case?
so not cactus. Like, I mean, we can beat cactus rank with this method, but we can't really beat border cactus rank, at least not so much. There is it is only minimally, it can be only minimally better than border cactus rank, but it also has like really much larger space, which is not seen by cactus rank, and it's the problem is we didn't write it down carefully, but I think it's should be. Where should I go? Maybe like this. If you add saturated, then you're in neither, right? There is saturated is first of all too weak to work to define border rank, and also to the Hilbert function. You will need more different Hilbert functions as well to work with that. But the main problem is that. I think if you take T in A, tensor B, tensor C, so a tensor, a non-S tensor, I think we've worked out examples, if these spaces are sufficiently large, that you can have I contained in annihilator of T with correct Hilbert function. And then something like, with the correct Hilbert function for R, something like of the order of M square, is the dimension of A, dimension of B, dimension of C. Such that is it M square? Maybe it's twice M plus something, such that everything, so essentially for all T, this thing happens. So I don't remember exactly the argument that it was showing that if you go with R large enough and you forget this condition about being a limit of ideal of points, you essentially get essentially the same ideal that works for all tensors. There's like a very minor difference in the ideals. So it's kind of, I mean, you really need to understand this condition eventually. So, it was less than the cactus rank, much less than the cactus rank. Yes, please.
Can you get more information on the border rank if you impose stronger conditions on the group B? Instead of solvable, you take something stronger, and you determine the border rank in some cases?
Well, So this is, I guess, a good question to Mateusz. So they have, Mateusz and Landsberg, they used more of group action than just the solvable group to show that there is always a appropriate closed orbit of G, but then this orbit is not a point. It's can be something much larger, and it's there's no direct translation on the ideal. We'll say that you will get a family of ideals that's invariant under G, and you don't get easy dimensional checks. So here I reduced it to a one Borel fixed ideal, and that makes it possible to calculate and possible to work with. But with the G action, I will get a family of ideas, fine, okay, maybe it's better, but I can't really work with them in a linear algebraic way. So you need more geometry, which doesn't really help to solve the problem. At least we were not able to do that.
In the cases where I does not define some defined scheme, does it make sense to associate it in our linear algebra, like homogenizing by some variable? And if so, would that be Konstanz?
If you dehomogenize it,
Yeah, do you have any meaningful object there?
you will get just the underlying scheme. If you dehomogenize it, the homogenization will kind of do the same as saturation. So you are back to the same smoothable rank. So smoothable rank does not have to be evinced by Gorenstein schemes, but it can be evinced by anything. But roughly, yes, you get back the scheme. So the homogenization like forgets the non-saturated part because you. Yeah, I guess it's 5:10, so I won't keep going. Thank you.